Okay, so our next unit within the energy unit is going to focus on Hooke's law, which is specific to springs and rubber bands and things of that sort. And we would conclude whether or not a rubber band actually obeys Hooke's law in class if we were doing normal labs. But last week we defined potential energy as the energy due to either a position, gravitational potential energy, if the position is above Earth, then that has some potential energy. But elastic potential energy, that is going to be energy that's stored in a spring. And that's going to be equal to the work done compressing or elongating the spring. Now, it can get a little tricky with what exactly compression or elongation means, but what we're going to define it as the displacement from the equilibrium position. And I have some pictures that'll help in a second. Equilibrium, that's an I there, position. Okay, and it's important to note that springs do have elastic limits. If you take a spring and you stretch it, really far and exert a lot of force on it, it's not going to act like a spring anymore. It'll get ruined. But while it's under, its compression or elongation limits, it'll follow Hooke's law, which is the relationship between the force exerted and the displacement that the spring is either compressed or elongated. So Hooke's law is going to be defined as the force exerted on a spring equals K X, where K is the spring constant. So each spring has a specific spring constant. So that really just tells us the stiffness of the spring. So a really high spring constant is going to be a very strong spring, and then a very low spring constant will be very easy to move that spring. And a spring constant has units of newtons per meter. And then X is either the compression or elongation. So that's going to be always in meters. Okay, and we're going to do this experiment virtually, but you can vary the amount of force that's applied to the spring and measure the distance that the spring is stretched or elongated. So I'm going to give you a second to pause the video, plot these points on the graph in the notes, and then we will go over it in 1 second. Okay, so I plotted my points. Make sure that you have units on the axis, and your graph always has a title. Here I do not have a way to draw a perfectly straight line, but I could do a little better than that. Remember, a line of best fit, it should be very straight. It does not have to pass through all of your points. So the way that you could find the spring constant of this spring, well, F equals Kx. So if I were to rearrange this and solve for K, I would get K equals F over X. And here on the y-axis we have force, and on the x-axis we have x, or distance. So for a force versus, so F versus x graph, the slope is equal to the spring constant K. And that's going to be a very important relationship to know moving forward. And obviously, as the more force is exerted on the spring will stretch a little further. So here we have a horizontal spring. This is where the spring is happy, so it always wants to be there. But if we exert a force on it in this direction, it's going to stretch a distance x. So here is that distance. And we can see another picture here, which is a vertical. So sometimes the questions, they'll put like a meter stick here, and they'll have, you know, different things noted. But this is our 0 point. So where the spring is in equilibrium is where we will measure from. So the x here, as you can see marked by extension, would be here. And that's what we would plug into F equals kx. Okay? And the last thing that is involved with Hooke's law and springs is the potential energy stored in the spring. And like we said, that's due to a position or a condition. So potential energy of a spring, it's not going to be due to the height, but it's going to be due to the spring constant and the amount that it's either compressed or stretched. So like gravitational potential energy, the higher something is, the more potential energy it has. But with a spring, the stronger the spring and the more it's stretched, is the more energy is going to be compressed in that spring. So this formula is given to us by potential energy. Whenever we're talking about Hooke's law or springs, we put that little S there. And it's similar to the kinetic energy formula in a way that it's set up, 1/2. And we have the spring constant, which is Newton meters, times x squared. Okay, so we have PES equals 1/2 kx squared. Now, this is energy, so it's definitely still measured in joules, just like all other forms of energy. So for the sample problem, determine the potential energy stored in the spring in the previous sample when a force of 2.5 newtons is applied to it. So in order to do that, we need to go back to this problem and we need to find the slope of this line. So I'm going to go ahead and do that. Looks like this point's on the line and this point's on the line. So however you're comfortable doing it, you can do rise over run if you'd like to do it that way. Or you can do the traditional change in y over change in x and calculate the slope that way. So I'll give you a second to do that on your own. And when you do that, you should get 25 Newton meters. Okay, so here, this spring, we have a spring constant of 25 newtons per meter. Okay, so here, we want to know the potential energy stored in it. I'm going to make sure I want to plug in with units. We have that. But wait, the problem doesn't give us x squared, and that's why it's okay to go ahead and start solving something, but then if you don't have it, okay, well I got to take a step back and figure this out. So we do have the relationship of Hooke's law, but we're given that a force of 2.5 newtons is applied to this spring. So since I know the spring constant, I can figure out how far this spring is going to compress or elongate based on the spring constant. If I peek back to the graph, I could take a quick, guesstimate at it. So if I go to 2.5 newtons, okay, so it's probably somewhere around here. It's probably close to, 0.1 meters. But, let's really figure it out. So we have 2.5 Newton force. Okay, we had a spring constant of 25 Newton meters. And yep, looks like we're going to get that. So we get an x, or a elongation, of 0.1 meters. Now that I found that, I can go back to my elastic potential energy formula, figure that out. So I could plug in that 0.1 meters. move over this squared sign. Okay, and you can just plug that into your calculator, do 0.1 squared times 25 times 0.5, and we should get an elastic potential energy of 0.125 joules. And there we have it.